Are there ballistic trajectories connecting Earth to any other planet or moon? I may as well state it another way, connecting orbits around any planet or moon with any other. My answer as a conjecture is that yes, possibly. So we're going to consider the restricted three-body problem and go over some old results and some new results, mostly about phase-space transport phenomena that are known. So, for instance, ballistic capture and escape through the Lagrange points and navigating around mean motion resonances. And then try to patch solutions of the four-body problem using three-body solutions. The talk is one long argument. So we're first just going to consider some planar models because those are the easier ones to discuss, but much of this carries over to the full 3-degree of freedom problem. So we all know, hopefully, about the restricted three-body problem where you've got a point mass and an effective potential plus a Coriolis force, usually viewed in the rotating frame with everything non-dimensionalized. And the planar equations of motion are well known to many of us. And there's an energy integral. I'll often use the energy, so this is the Hamiltonian, which of course is -1/2 of the Jacobi constant, and I'll go between those as necessary. A trajectory connecting a loose orbit between the Earth and the Moon isn't too hard to find. This is actually an earlier result where starting out at a geo-radius orbit, you do one burn, but then you get onto this loose orbit. This is in the rotating frame on the right and the inertial frame on the left. And you can see that we're waiting for the phasing to be right for this loosely bound orbit about Earth. Once it gets caught up with the Moon, or actually goes past the lunar L1 point, now we're on an orbit around the Moon. And you can partition realms of possible motion just using the usual Hills region. So based on whatever the energy is, the phase space is roughly partitioned into three large regions, which I'll call realms. So the Earth realm is the phase space around the Earth, the Moon realm is the phase space around the Moon, and then you have the realm exterior to them both. And this energy E determines that connectivity. So if we look at the lowest energy, this would be where it's just isolated around M1 and isolated around M2. Once you get to an energy above L1, if there's a bottleneck that opens up and now transport is possible between the two masses. When we get to case 3, now it opens up with L1 and L2, both have bottlenecks. This is probably the case I'm going to focus on the most. As you increase beyond L3, the zero velocity curves bounding this forbidden region are shrinking into tadpoles, and once you get above L4 and L5 energies, anywhere in the plane is accessible according to an energy arc. But how do you actually move between those regions? There's some work that goes back to Conley and McGehee in the 1960s, where they were considering how to get to the Moon cheaply. And we're looking at Lyapunov orbits around L1. They're unstable, and they have stable and unstable manifolds of a cylindrical geometry. And they speculated on the use of these for low-energy transfers. The Apollo program had just started in the United States, and there was a lot of excitement about going to the Moon. So that's where they had their initial motivation. And this is a schematic of what it may look like in phase space, where you've got, at least on an energy surface, right? If we have a 4-dimensional phase space, we have a 3-dimensional energy surface. These tubes have the topology of a cylinder, and they can go from one side to the other. So just going back to that initial trajectory, going from the Earth to the Moon, we could see again, at least in the rotating frame, the last little part went past the L1 point because the energy was large enough for that to happen. So these transitions between different realms have to occur, at least in this case 3 case or the case 2, within one of these cylindrical manifolds. And we call these tubes, and what they do, tube dynamics. And there's a lot of work on this, like I said, starting with Conley and McGehee, but then a lot of work in the 80s by a group in Barcelona and others since then. These motions are just the result of the equilibrium point being an index 1 saddle and an n degree of freedom Hamiltonian system. So the eigenvalues, there's one purely real pair, and then the rest are purely imaginary. So we say it's a saddle center type. And for any energy that's above, I call the excess energy, the energy above the saddle point itself, there's a normally hyperbolic invariant manifold, which has the topology of a 2n-3 sphere within the energy surface. For the case of just 2 degrees of freedom, This normally hyperbolic invariant manifold is just a periodic orbit. But it's a periodic orbit that's unstable. It has both a stable and unstable direction, so we have these trajectories that are winding onto and winding off of it, the stable and unstable manifolds. And they enclose transitioning trajectories. So they enclose trajectories that go from one side of the Lagrange point to the other. And this just shows a cutaway. We look at that cutaway in further detail. We're looking at just a cross-section. So the dot in the middle is the Lyapunov orbit. And then we have trajectories in green that are asymptotic to and away from that point. The blue trajectories, we call those non-transitioning because they go back to their region of origin, and the red ones are transitioning. So giving another view, label them B for bound orbits, T for transition, and NT for non-transition. This is looking in the eigenspace near the equilibrium point. We look in physical space, then we could match up what these orbits look like in their position space projection. So the bound orbits are Lyapunov orbits. We've got the green trajectories winding onto and off of it. And the transition trajectories, which are of most interest to me here, are the ones that go from one side to the other. So these are the mechanism for ballistic capture, at least in the case 2 and case 3 energy regimes. Because what tends to happen is once a trajectory passes through here, say from the exterior region, it gets onto a loosely bound orbit, meaning it's got a negative Keplerian energy with respect to the secondary body. And the way that we typically look at these and try to compute things related to these tubes is we take a Poincaré-section that's transverse to them and look at their intersections. So in this case, we've got two Poincaré-sections, U1 in the Earth region and U2 in the Moon region, and we can patch things up there if we wanted to make some interesting trajectories. Again, these tubes are general. They're just a consequence of being an index 1 saddle. They're ubiquitous in chemistry. So there's a lot in the chemistry literature about this. It's related to state transition theory. And they persist even in the presence of additional massive bodies. You can see this numerically. We've also done some recent work on the time periodically perturbed restricted three-body problem to show that these structures really do exist, even when the primary body's orbit is eccentric. And it's observed in the solar system. The comet that initially got me interested in this is Oterma. So this is Oterma's trajectory in an inertial frame. We've got the sun in the middle. We'll have Jupiter going around. This is in an inertial frame. And so you could see this is from 1910 to 1980. So during that span of 70 years, it starts from outside the orbit of Jupiter, has a close encounter with Jupiter, which takes it inside for 3 revolutions, catches back up at Jupiter, and now it's on the outside again. So this is also a resonance transition. It goes from the 3-2 to the 2-3, passing by Jupiter. And of course, we can see more if we look in the rotating frame. We could see, at least during this time frame, that it gets close to the L1 and L2 points. Jupiter has this excursion, and then it goes out. And I'm also showing that this is in the case 3 energy regime. So bottlenecks have opened up around L1 and L2, and they're pretty narrow. So if we wanted to construct a trajectory that has the same itinerary as Oterma, in the sense that if we refer to the realm outside as the X realm, the realm around Jupiter is the J realm, and the realm around the sun is the S realm. At least the first part of what Oterma does, we could label that as XJS. And so really we're searching for an initial condition that has this itinerary. So how can we do that? First, we'll do it in 2 degrees of freedom, but this could be calculated in 3 degrees of freedom as well. So we're going to seek an area on an appropriate 2-dimensional Poincaré-section corresponding to this region. So now I'm showing 4 Poincaré-sections, and we'll use those as needed. If we now look at the tubes, stable and unstable manifolds related to the Lyapunov orbits around the L1 and L2 points. Green, I'm showing stable, red, unstable, and I'm just stopping them when they both reach a Poincaré-section. I've labeled these a particular way. The TXJ up here means this is a tube that's currently in the X region and is going to the J region. And just zooming in, and we could label all of these tubes appropriately. This one up here is a tube that's in the J region and is going to the S region. So an initial condition which is inside the boundary here of the tube will exactly do that in the short-term itinerary. So if we want to create XJS, we need to look at these two and look at their intersections. So this is coming from the X realm and going to the J realm, and then this is currently in the J realm and going to the S realm. We look on the Poincaré-section, and we can see that these two actually do intersect. The intersection may not be very big compared to the relative size, but it's still there. And we have ways of labeling this, right? We can just concatenate what we have over here to refer to this as XJS. Any initial condition chosen in this intersection region, if we follow it forward and backward, it should produce the desired trajectory. And so this is that exact trajectory. So it does XJS. That was just the first part of at least what we saw the comet do over 70 years. So if we extend this further, we can look at longer intersections to get larger itineraries. And you can see that this could go out infinitely, and then we get a Cantor set of individually labeled trajectories. But here, when we have a finite itinerary, we have an open set. So everything in this open set will do JXJSJ. We take an initial condition in there and integrate it forward in black and backward in the dashed line, and this is what we get. So we can create itineraries that match what comets do. We could also do this in 3 degrees of freedom. There, the set of bound trajectories, the normally hyperbolic invariant manifold isn't a circle, it's the 3-sphere. But we could still do it and find initial conditions that correspond to the desired itineraries, integrate this forward and backward, and we get the same kind of behavior, but now in 3 dimensions. And you could get other types of trajectories that get onto a loosely bound orbit around the secondary body. So here's an example of that. Now that we've established how ballistic capture works, and the time reverse of that would be ballistic escape, how do you navigate between different planets? Well, this is showing on a large scale the case 3 energy surfaces of the giant planets. And you can see that they intersect. So can we do something with them? They're basically following Tisserand curves. So this is just writing the Jacobi constant, but in terms of the semi-major axis and eccentricity. Are there any possible phase-space mechanisms for, say, going along one of these energy surfaces until you intersect the energy surface of another 3-body system, and then getting back down, so say going from the Earth to Mars? We'll consider the planar, concentric, circular, restricted 3-body problem. So this is where there's the central mass of the sun and then 2 planets. So M1, the sun, M2 and M3 being 2 planets that will idealize as being on circular orbits around M1. We'll patch the system as 2 circular restricted 3-body problems. So we'll first consider the point P in, say, M1, M2 and the particle. And then we'll go to M1, M3 and the particle. And we're going to use a model that's a bit easier to work with in the full phase space. So I'm going to assume that the particle is on a near Keplerian orbit. And in the frame, it's co-rotating with M1 and M2, so the usual rotating frame. We could write the Hamiltonian in terms of Delaunay-variable. And then the evolution is Hamilton's equations for the Delaunay variables. And of course, the Jacobi constant has to be conserved along trajectories. The evolution of G, Delaunay variable, looks like this, where if we use the Picard's first approximation, just to look at what's the change in G over 1 Keplerian orbit, we can do an appropriate integral and find out that the Keplerian energy change over an orbit is equal to delta G minus mu delta R, which if you combine those, we get that the change during 1 close encounter or during 1 period of the particle has the form of the mass parameter mu times a function of the argument of periaps in the rotating frame. So we call this the energy kick function. And it has as parameters the Keplerian energy and the 3-body energy. So just to explain what this diagram is showing over here, so this is the kick function as a function of omega. And you see that there's a peak and then a trough. This is odd in omega. So we've got, say, omega max and negative omega max. This corresponds to if the particle has a periaps at those 2 locations, that's where you get the maximum change in the Keplerian energy and therefore in the semi-major axis. So this is just showing a schematic of 2 test particles coming by. One has its close encounter at omega max, and it decreases in semi-major axis. Right? You can think of this as if you have your close encounter at omega max, you're having energy taken out of your orbit. Whereas if you have a close encounter here, the secondary mass is actually pulling you forward and adding energy. A nice intuitive understanding of that. Again, if you just slightly change the initial conditions of a particle, then you could get that the semi-major axis either decreases or increases if you do have a periapse near here. So often you don't have a periapse anywhere near where the kick function has large kicks. But what we'd like to do is, from that kick function, construct an update map that takes us from one set of orbital elements to the next. So using the average perturbation per orbit by the smaller mass and the secondary. And the cumulative effect of many gravity assists can be dramatic. Now, these aren't the usual gravity assists. This isn't a swing by used by Cassini or the Voyager missions, because it happens outside the sphere of influence. We're not getting closer to the secondary than L1 or L2, but we're outside. This is how we construct this update map. We're looking at the argument of periapse in the rotating frame and the Keplerian energy and updating it. So since omega is a circular variable, our phase space is the cylinder, and we've actually are constructing a symplectic twist map on the cylinder. So it has this form. This is from some work with Dan Shears several years ago. We could also identify this map, which we call the Keplerian map, as a Poincaré surface of section at periapsis in the orbital element space. So when the mean anomaly equals 0, that's what this is. So this is what the Keplerian map gives you if you take some initial conditions that are in the chaotic region and just iterate them many times, I think tens of thousands of times. So this is omega versus semi-major axis. So that's a bit easier to interpret. If you compare it with the numerical integration of the full system on the right-hand side here, you can see they're very similar. So this Keplerian map, you could treat it as an approximate fast orbit propagator. Because it is a symplectic map, it's just like the standard map, but I think has a richer set of dynamics. In particular, there are these resonances. There are mean motion resonances, stable ones and unstable ones. So I'm highlighting here an unstable mean motion resonance, black dot in the middle, and it's stable and unstable manifolds. You've got lobe dynamics or turnstile mechanisms taking things around the resonances, and you have a whole chain of resonances. So if we started at some initial condition appropriately chosen, then it could go around these resonances in just the right way that you get a decrease in the semi-major axis. And eventually this could get to the point where there's a natural ballistic capture by the secondary mass. So just to show this, I'm taking a line of initial conditions on the cylinder. I'm calling that gamma naught. And we'll be iterating this under the map. Under one iterate, it'll just look like the kick function. If we do two iterates, now this is what our curve looks like, the black curve. And what I'm trying to do is pick the initial condition that is decreasing the most. I want delta A to be the most negative. It seems to be around there. I guess it's actually around here. So if I zoom in on that region, and then I iterate 8 more times, so now I'm at gamma 10. So this is 10 iterates of the initial set, the initial circle around the cylinder. I have a region here that seems to be decreasing the most. So let me zoom in on that and iterate a few more times. Now I've got a point down here. We zoom in on that and iterate several more times. So now after 25 iterates, I've identified this initial condition that I've labeled B as the one that has decreased the most under 25 iterates. So that initial condition is this triangle up here embedded in the chaotic C. And after 25 iterates, it has ended up at this square. And if you look at the trajectory in the inertial space, this is what you get. We started out in a large orbit, but after several passes, we're decreasing the semi-major axis. Actually, we're decreasing the apoapse and keeping the periapse the same. Now, this is connected naturally to the ballistic capture regime, because when these tubes intersect the Poincaré-section that we're speaking of, they still are topologically disks. And I'm calling this an exit, because it's an exit from this Poincaré-section. So if some initial condition eventually through several iterates makes it into here, then it goes through the bottleneck around L2 and would make it into the region around the secondary. In this case, I'm thinking of the Jovian moon. So if we're looking at the Jupiter and the Jupiter moon system, this is where the Poincaré-section at periapsis is for this little teardrop shape. It's kind of hard to see. But if you're inside there, then you'll naturally be captured onto a loosely bound orbit. Just to give an example of the way things might work going between planets, I'm looking at a mini solar system, Jupiter, and its several moons. Specifically, I'm really just going to look at the icy moons. So can we construct an orbit that is unpowered? So we're just looking for the right initial conditions so that we orbit Callisto, then Ganymede, and then Europa. And we can't. This is the final trajectory here. If you have an initial orbit that grazes essentially the orbit of Callisto, then you could get loosely bound around Callisto and then go on to Ganymede, bound around Ganymede, go on to Europa. And this is what it looks like if we consider the semi-major axis and eccentricity space. And you can see these curves of constant energy, so Tisserand curves, and here's the spacecraft path. These places where there's an intersection between two different three-body systems, something interesting happens there. We call that the switching orbit, and I'll talk about that. So the switching orbit, if we have, say, Jupiter, and here's one of its moons, we pick an initial condition so that under perturbations by just this moon, so we're looking at the Jupiter, M1, and particle three-body system, we can decrease the periapsis to the point where it almost grazes this inner moon. And so we call that the switching orbit S. And at the point that the switching orbit gets perturbed by M2 and brought closer into M2 so that the apoapse is now farther away from M1, now the particle is under control of this new three-body system. That's what I mean by switching orbit and patching solutions. So this is an animation that shows that the blue trajectory is the particle, and the outer moon is in red. What we'll see is that this next encounter, the phasing is just right so that the periapse decreased, and then the interaction with that inner moon decreased the apoapse. So now this particle has gone from control of the outer moon to the inner moon in terms of the three-body system. And if we look at this sped up tremendously, we're looking now at the same situation going between two moons. I think this is Ganymede and Europa. And looking at the semi-major axis versus eccentricity. So the semi-major axis right now, it's going upward because we're along one three-body system, the one with the outer moon. And then once we reach a switching orbit, which we're not quite there, you'll see when it grazes that inner moon that we're very close. Once it grazes that inner moon, then there's a transition to control by the inner moon, and the semi-major axis and the eccentricity will decrease together. So I think the switching orbit is about to occur, and there we go. So now it's going down, and eventually this trajectory will get into one of the tubes of capture leading to the inner moon. And this is showing that trajectory going from Callisto to Ganymede to Europa in terms of the semi-major axis, but also the geocentric distance. And this takes, you can see here, several years, about 1,600 days. It's on the order of tens to hundreds of the orbital periods of the moons. We can expect that for the outer planets, we might find something like that. There is an issue, though, that we have to be aware of, that some resonances can actually block transport completely. So we've got this phenomenon called rotationally invariant circles. These are tori that completely block the cylinder, right? The two sides of the cylinder here can be identified. And so there's no way to cross one of these rotationally invariant circles. They correspond to a resonance, but at least in our case, we think of them as blocking transport. So if we have any blockage of transport, this could inhibit the transition between two planets. So if we look back again now at case 3, and I'm writing in terms of Jacobi constant, but the main thing is we've got the Hills region has opened up, so now there's bottleneck around L1 and L2. The only constraints we've dealt with so far are these zero velocity curves, but of course there's other things in phase space that might block. So these bounding rotationally invariant curves, or RICs, provide an additional constraint on the motion. This isn't new. This was proven to exist by Richard McGehee in his 1969 PhD thesis. We'll refer to them as McGehee tori. He proved they exist, but didn't actually calculate them. So we have a way to compute them. I'm just showing projections of tori in the energy surface onto the position space. So we've got some additional constraints on how far the particle can go, both in the exterior and in this interior realm. The way that we find these is using our 2D symplectic map. The blue dot here is an initial condition that's iterated, several thousand iterates, and you can see at some point it reaches a closed curve. So that closed curve, not sets of closed curves, those are other resonances we're talking about. It's an actual function of omega. So we can find that, and we call those the bounding RICs, or sometimes just RICs. So these are the boundaries to transport. So here's another one that was found in red, an identified RIC in the phase space. And like I said, these correspond to, up in the energy surface, a torus that actually blocks motion on the energy surface. You project it into the rotating frame position space, you get this middle figure, and in inertial space, it looks like the figure on the right. So it's just one particular orbit that's a resonance that blocks the phase space, blocks the energy surface, I should say. If we calculate where this first RIC is, we can do this for many values of mu. This is looking at the first RIC. What we're computing is the close approach of this RIC to the secondary. And we get something that seems to fit the power law, about 0.7 mu to the raised to the 0.242 power. And what we're actually computing is the first RICs, it's these white circles, and you can see that there's regions where they're completely flat because they are associated with resonances. If we calculate some average curve, that's our best fit curve here, it's shown dashed. So it's not just first order resonances, at some point 2, 3, 6th order resonance shows up. So we consider this another definition of a chaotic zone radius, somewhat analogous to Wisdom's from 1980. So we've compared it here with sphere of influence, which is mu raised to the 2/5 power, the Hills region, which is raised to the 1/3. This other one from Wisdom, which is mu to the 2/7. Ours, we have mu raised to 0.42. And for some range of mu, below about mu of 10 to the -6, our definition of a chaotic zone radius is actually the largest. There may be something to it. Now, the reason I took this little digression to talk about these bounding RICs is because, like I said, they can block transport and make it so that you can't move between planets. So when is a transfer possible? Well, it's when the switching orbit is between the RICs. So we have a way to calculate what that switching orbit is. It's just where the two Tisserand curves intersect. If we have an outer planet, say at a radius of 1, here's its interior RIC. And I'm just showing this in schematic. If we have another planet, say at a semi-major axis of A, then it will have an exterior RIC. And as long as our switching orbit is in between those two, then a transfer should be possible. So we tried this for an Earth to Venus transfer, where we started at the switching orbit and integrated backward under the Earth system and forward under the Venus system. By system, I mean the Keplerian map with the appropriate mu. And we do find that something gets captured. So each of the dots here is one iterate. But in this region, the lower half, this was with the Sun-Venus particle system, and above here is the Sun-Earth particle system. This is what it looks like in terms of semi-major axis in AU versus the number of iterations. So this isn't exactly years, but this transfer took 1,400 years. So this is what it looks like in the AE space. So we start with a departure from the Earth L1 we hop on an orbit, and then this crawls along the curve till we intersect the energy surface with Sun, Venus, and then it crawls down to Venus. So this is what the entire trajectory looks like. Again, 1,400 years, so it's on the order of hundreds of times the period of the primaries, which I think will be related to the very small mu value here. But I chose this connection, so this shows, okay, from the Earth orbit, we can go to Venus. From the Earth orbit, we can go to the Moon. I think we'll be able to go from an Earth orbit to Jupiter. And of course, there are other transfers between the planets could exist, and some might be related to comets or this class of very few objects called centaurs that are moving between the outer planets. This is one particular comet that just does something interesting, Smirnova-Chernykh. It starts out in a large orbit. The grazes the orbit of Saturn, but it has a close encounter with Jupiter, and then it's definitely under the control of Jupiter until at least 2100. So when I ask, are there ballistic trajectories connecting Earth to any other planet or moon, I may as well state it another way, connecting orbits around any planet or moon with any other. I think it's possible. The dynamical mechanisms in the restricted three-body problem enable this. The location of the bounding Ricks, or I might say McGehee tori, could be a limiting factor, especially for the small mass parameters. And if this is true for the solar system, does this have implications? I don't know. It's an open question. I've got some references here, and I'll just leave it at that. So thank you for your attention.
If you appreciated this video, please like and subscribe. There are links and other materials in the description.